Good morning. Stream should be coming up and online. And we're up. Perfect. Sound seems to be working fine, or at least the indicator is working. Is my mobile dashboard working? That's a good dashboard. There it is. There it is, so I can share this out. All right. I think that might be a good future project with this. Is when I start going live, maybe a REST application that will share this out automatically. And due diligence done. Let's really quickly test my my chat here. Stream chat. Good morning. Good morning. Autocorrect don't need you this morning. Yep, and it's working. Perfect. All right, so for today, we're going to continue on with chapter 15. Last week, we were just getting to dropping a value early with standard memory drop. And what we had done with code is go through and create a box, specifically a sort of, our own version of a box. So a box is a standard, sort of like a memory constructor. It's a smart pointer. And what that means is we're able to put any kind of data inside of it, and it stores that data on the heap, even if it was going to store it on a stack. And then that way we can do some interesting tricks with it. Specifically, we can then do these dereference, dropping it like in specific places. Good morning, good morning. Some would say we're stacking the stack. Yeah, or we're just throwing the stack on a heap. We're heaping the stack. I don't know. I think it gets a little bit confusing because we have to use all the terminology to really explain what's going on. I'm still not completely sure of when I would want to use a box or a smart pointer. I think that will probably come with time. And then stacking. Last week you said you were going to take a couple days off of work to build some cool stuff with Rust. You're making a crappy pun. I don't know. I thought it stacked up. No, that's even worse. How was your Rust? How was your Rust playtime? Like, did you make something cool? I would love to find out and see what you did. Gonna come here, dropping value early. We're halfway through this section right here, and also we're about halfway through chapter 15 too. All right, so let's go ahead and get started. Dropping a value early with standard memory drop. Unfortunately, it's not straightforward to disable the automatic drop functionality. Disabling drop isn't usually necessary. The whole point of the drop trait is that it's taken care of automatically. Occasionally, however, you might want to clean up a value early. One example is when using smart pointers that manage locks. You might want to force the drop method that releases the lock to run so other code in the same scope can acquire the lock. Rust doesn't let you call the drop trait's drop method manually. Instead, you have to call the standard memory drop function provided by the standard library. if you want to force a value to be dropped before the end of its scope. If we try to call the drop traits drop method manually by modifying the main function from listing 1514, as shown in listing 1515, we'll get a compiler error. And so here we're just saying C. It's our custom smart pointer. We put some data in it, and then we do C.drop. And we get an error saying, hey, you can't do that. You only made it to the chapter I was talking about method chains. The wife didn't let me get as much playtime as I would like, but the taste of Rust I did have really makes sense. Really makes you want to play with it more. Yeah, no, highly. It's the same thing for me. I want to do things after work. I want to do other things, even if I don't necessarily have time for it. Because I have to keep my other skills up too. So, after work, I'm usually in the domain of JavaScript and web development. So I'm doing that as well. But if you do make anything, definitely show it off. I know other people who are interested in getting into Rust as well. And I think like just having more people play with it is gonna help the future of the language, because the more people who use it, the more it's gonna get support, the more it's going to get cool things added to it. This error message states that we're not allowed to explicitly call drop. The error message uses the term destructor, which is the general programming term for a function that cleans up an instance. A destructor is analogous to a constructor, which creates an instance. The drop function in Rust is one particular destructor. Rust doesn't let us call drop explicitly because Rust would still automatically call drop on a value at the end of main. This would be a double free error because Rust would be trying to clean up the same value twice. We can't disable the automatic insertion of drop when a value goes out of scope, and we can't call the drop method explicitly, so we need to force a value to be cleaned up early. We can use the standard memory drop function. The standard memory drop function is different than the drop method in the drop trait. We call it by passing the value we want to force to be dropped early as an argument. The function is in the prelude, so we can modify main in listing 1515 to call the drop function as shown in listing 1516. So in here, the difference is instead of C.drop, it's then drop and then pass in whatever like the memory is. So if I understand this correctly, C is sitting on a stack, but it's sitting on a stack in a known size because it's just pointing to some place in memory. So we're able to pass it like the location in stack, and it just handles it. I guess that answers a trait override. Yeah, I think it does. We're sort of able to override it, but not fully. Running this code will print the following. Custom smart pointer created, dropping custom smart pointer with data, some data, custom smart pointer drop before the end of main. There is a siren outside. I'm gonna close the window really quickly. And I'm back. All right, so the text dropping custom smart pointer with data, some data, is printed between the custom smart pointer created and custom smart pointer drop before the end of main text, showing that the drop method code is called to drop C at that point. You can use code specified in a drop trait implementation in many ways to make cleanup convenient and safe. For instance, you could use it to create your own memory allocator. With the drop trait and Rust ownership system, you don't have to remember to clean up because Rust does it automatically. And I guess like that's the thing, is because Rust is doing this automatically, how often would we want to potentially manually like do this memory management? The only thing I can think of is if I'm using like gigantic data sets and my function is really large, and so therefore it's not being passed around to be like cleaned up, that might maybe then. You also don't have to worry about problems resulting from accidentally cleaning up values still in use. The ownership system that makes sure references are always valid also ensures that drop gets called only once when the value is no longer being used. Now that we've examined box T and some of the characteristics of smart pointers, let's look at a few other smart pointers defined in the standard library. Because they sort of mention like, oh, you can use box or you could use these other things too. In the majority of cases, or rather RCT, the reference counted smart pointer. In the majority of cases, ownership is clear. You know exactly which variable owns a given value. However, there are cases when a single value might have multiple owners. For example, in graph data structures, multiple edges might point to the same node. And that node is conceptually owned by all the edges that point to it. A node shouldn't be cleaned up unless it doesn't have any edges pointing to it. To enable multiple ownership, Rust has a type called RC generic type, which is abbreviation for reference counting. The reference counting type keeps track of the number of references to a value, which determines whether or not a value is still in use. If there are 0 references to a value, the value can be cleaned up without any references becoming invalid. Imagine RCT as a TV in the family room. When one person enters to watch the TV, they turn it on. Others can come into the room and watch the TV. When the last person leaves the room, they turn off the TV because it's no longer being used. If someone turns off the TV while others are still watching it, there would be an uproar from the remaining TV watchers, because that never happens in a family, right? We use the RCT type when we want to allocate some data on the heap for multiple parts of our program to read, and we can't determine at compile time which part will finish using the data last. If we knew which part would finish last, we could just make that part the data's owner, and the normal ownership rules enforced at compile time would take effect. Note that I guess it's reference counted T is only for use in a single-threaded scenarios. When we discuss concurrency in Chapter 16, we'll cover how to do reference counting in multi-threaded programs. I could see me using this to clean up secret keys out of memory, so I could know it was freed right then. But like, the next question is, how important is it to free it up like right then? Because oftentimes you need it for any of the HTTP calls you're going to be doing. And each of those HTTP calls are going to need the key. So unless like if we do the key once at the very beginning, and then we don't need it anymore. But I could also see like if we just shift it off to a function, we give ownership to it, and as soon as that function is done, it's gone and it's over and it's cleaned up for us. And if we don't want to, then we're kind of leaving it in memory the entire time. So I don't know. I'm probably missing something. I'm probably like not seeing like a potential way to do it because I haven't used smart pointers before. And I haven't really like thought about this automatic memory management in this way before starting to play around with Rust either. Let's return, or using RCT to share data. Let's return to our cons list example in listing 15.5. Recall that we defined it using box T. This time we'll create 2 lists that both share ownership of a third list. Conceptually, this looks similar to figure 15.3. So here are 2 cons lists, B and C, and they're both going to be owned by A. I think that's what I'm seeing here. But we can't let any of them die until we reach the end, right? We'll create list A that contains 5 and then 10. Then we'll make 2 more lists, B that starts with 3 and C that starts with 4. And C lists will then continue on to the first A. C lists will then continue on the first A list containing 5 and 10. In other words, both lists will share the first list containing 5 and 10. Okay, yeah, so B points to here, C then points to here. Trying to implement this scenario using our definition of list with box T won't work, as shown in listing 1517. So if we have our enum list, we have cons I32 box list. We say let A equals cons 5. That'll be this first one right here. Can't get them both on the same screen. 5, and then its second value is going to be box new cons 10. So that would be here. And then box new nil. So that we're creating this one first. And then let B equals cons 3. Then box new A. And C is cons 4, box new A. The problem is that we're handing ownership over, so it won't let us do this for C. When we compile this code, we get this error. Move occurs because A has a type list, which does not implement the copy trait. The cons variance owns the data they hold, so when we create the B list, A is moved into B, and B owns A. Then, when we try to use A again when creating C, we're not allowed because A has been moved. We could change the definition of cons to hold references instead, but then we would have to specify lifetime parameters. By specifying lifetime parameters, we would be specifying that every element in the list will live at least as long as the entire list. The borrow checker wouldn't let us compile let A equals cons 10 and reference to nil. For example, because the temporary nil value would be dropped before A could take a reference to it. Instead, we'll change our definition of list to use RCT in place of box T as shown in listing 1518. Each cons variant will now hold a value and an RCT pointing to a list. When we create B, instead of taking ownership of A, we'll clone the RC list that A is holding, thereby increasing the number of references from 1 to 2 and letting A and B share ownership of the data in that RC list. We'll also clone A when creating C, increasing the number of references from 2 to 3. Every time we call RC clone, the reference count to the data within the RC list will increase, and the data won't be cleaned up unless there are 0 references to it. So let's actually start a project in doing this. So it's RC is what we're playing with. Don't need you. Cargo new RC. Code. All right, so what are we doing here? We're going to first create an enum list that is the same thing as cons, takes an I32, but then it's RC list, and then nil. So enum list, and it's cons I32 and then RC list. So cons I32 tuple, and then RC. Is it RC like that? It is. I'm getting It doesn't like this. Cannot find type RC in a scope, not found in a scope. Okay, so it's not telling me where to grab it. Let's go ahead and run this. And you didn't bring RC in a scope. Yeah, I was hoping like their example didn't say where to bring that in. So let's just run cargo run, and it will probably tell me where to bring it in. Use standard RC. Damn, the error checking beating me. You can't, well, I was gonna say you can't beat the error checker, but we found out that actually the error checker in VS Code does tend to be a bit error happy. It sometimes likes to show errors when there's not any errors or when I fix them. Okay, so we have our enum list, and then what we want to do here is, oh, interesting. I didn't even notice the use list cons nil and then use standard RC. This is interesting. For some reason, I thought we had to do the uses above where they are, but we can use them anywhere, including the bottom. I don't know how I feel about that. I kind of like the idea of having the uses up at the top when possible, but I also understand that this is not easy because like they were trying to bring in cons and nil. But I have to say the error checker is one major thing I love about Rust. It's like no stupid, and basically writes the code for you. Yeah, no, it totally does. The only problem is VS Code's error checker version is just like almost there. It like doesn't quite show you everything, so you still have to run that yourself manually. I'm just not gonna run this use list. I think that this is a little bit confusing to bring out cons and nil so that we could just use it without the list. I understand why they're doing it to make it less typing in here, but I don't know if I don't think I like it. But okay, so in our function main, let a equals, so it's going to be RC new. So we're going to create this new RC. I'm going to hand it the list cons with 5 and then RC new. So let's do this one step at a time. So we're gonna say let a equals, so it's gonna be RC new, and its value is going to be list cons, and the first one is going to be 5, right? It's 5 and then a new RC new. So 5 and then RC new, and what was the next number? 10 and then nil. So 10 and then RC. Did I do this right? RC new is a list cons 5, and then the other one is going to be a new list cons. Yeah. There, I think I did that right. Okay, so RC new list cons. So it's a list by 32. It's RC new list cons 10. Yeah, that's what I was just thinking about. So, okay, right, because I was like getting tripped up on the order of when I want to do that. But yeah, it's list cons, and then this is going to be 10, and then RC new nil, right? No. Yes. List nil. All right. Got it. Now, of course, A is not being used, but that's okay. This is terrible. All right. So let B equals, it's going to be our list cons, the 3, but then we're going to hand it the RC, but telling RC to clone a reference to A. And the real thing is that it's not really cloning it. It's just keeping it, it's just adding it and saying like, well, okay, we want to increase the counter for the reference. So let B equals, and it's going to be a list cons, so list cons 3, and then RC clone a reference to A. RC interesting. I'm not seeing a clone in here. This is just lowercase. So clone and a reference to A. All right, that seemed to be fine. And then the exact same thing for C. So let C equals list cons. And what was this? This is 4. 4 RC clone and a reference to A. We need to add a use statement to bring RCT into scope because it's not in the prelude. In main, we create the list holding 5 and 10 to store it in a new RC list in A, or RC list in A. Then, when we create B and C, we call the RC clone function and pass a reference to the RC list in A as an argument. We could have called A.clone rather than RC clone, but Rust convention is to use RC clone in this case. The implementation of RC clone doesn't make a deep copy of all the data like most types implementation of clone do. The call to RC clone only increments the reference count, which doesn't take much time. Deep copies of data can take a lot of time. By using RC clone for reference counting, we can visually distinguish between the deep copy kinds of clones and the kinds of clones that increase the reference count. When looking for performance problems in the code, we only need to consider the deep copy clones and can disregard calls to RC clone. So I think the big thing here is that if we have large data sets and we want to sort of like have these different copies of it, we can sort of not do deep copies but then have copies. The only problem is if I want to mutate one and not the other, then this won't work. Cloning an RCT increases the reference count. Let's change our working example on listing 1518 so we can see the reference count changing as we create and drop references to the RC list in A. In listing 1519, we'll change main so it has an inner scope around list C. Then we can see how the reference count changes when C goes out of scope. All right, so let's see. We create A, and then we're going to say print line count after creating A equals RC strong count, and then a reference to A. And we're going to do that throughout as we do this. Also, we're going to do a block for C so that this goes out of scope right away, and we'll see the count to go down maybe. So let's do that. I guess if I can't do that up here because it doesn't exist yet. So we're going to do a print line reference count for RC A. And so this is going to be RC So this one does have strong count, and we could pass it a reference to A for what I want it to be counting. And on top of that, I'm now going to be able to copy and paste this code and do it over and over again. So in this time, we're going to put this in here. Interesting. So we don't care about like B and C, even though we're creating them. But I guess, yeah, it doesn't really matter. And so in here, Add you, and tab you in, and create just a block here, so that way we come into here, it has access to the outside block, but then this C is going to go out of scope right away. So let's run this and see what happens. Okay, so reference count for RCA. Let me make this a little bit bigger. Okay, reference count for RCA. We start with 1. That's at this point in time we have 1 because we've just put one thing into it. Then 2 because we added in the second list. Then 3 because now we're inside this block, and now we have the two parents essentially now pointing to the single child. Then we're back to 2 again because this went out of scope, and so it got dropped inside of RC. It was paying attention to it. At each point in the program where the reference count changes, we print the reference count, which we can get by calling the RC strong count function. This function is named strong count rather than count because the RCT type also has a weak count. We'll see what weak count is used for in the preventing reference cycles section. This code prints the following. So it's the same thing that we did. We can see that the RC list in A has an initial reference count of 1. Then each time we call clone, the count goes up by 1. When C goes out of scope, the count goes down by 1. We don't have to call a function to decrease the reference count like we have to call RC clone to increase the reference count. The implementation of the drop trait decreases the reference count automatically when an RCT value goes out of scope. What we can't see in this example is that when B and A go out of scope at the end of main, the count is then 0, and the RC list is cleaned up completely at that point. Using RCT allows a single value to have multiple owners, and the count ensures that the value remains valid as long as any of the owners still exist. Via immutable references, RTC allows you to share data between multiple parts of your program for reading only. If RTC allowed you to have multiple mutable references too, you might violate one of the borrowing rules discussed in Chapter 4. Multiple mutable borrows to the same place can cause data races and inconsistencies. But being able to mutate data is very useful. In the next section, we'll discuss the interior mutability pattern and the ref cell T type that you can use in conjunction with an RCT to work with this immutability restriction. Right. Ref cell T and the interior mutability pattern. Interior mutability is a design pattern in Rust that allows you to mutate data even when there are immutable references to that data. Normally, this action is disallowed by the borrowing rules. To mutate data, the pattern uses unsafe code inside a data structure to bend Rust's usual rules that govern mutation and borrowing. We haven't yet covered unsafe code. We will in Chapter 19. We can use types that use the interior mutability pattern when we can ensure that the borrowing rules will be followed at runtime, even though the compiler can't guarantee that. The unsafe code involved is then wrapped in a safe API, and the outer type is still immutable. Let's explore this concept by looking at the ref cell T type that follows the interior mutability pattern. I can't wait to learn ref cell. It feels like it's the answer to every question ever asked on Reddit. I mean, it does feel like there's a lot of those. Well, I feel I'm going to go into unsafe territory now to do what I want to do. And like sometimes when I'm reading those, I can't help but wonder if that's because we're sort of like trying to bend Rust into like another pattern that we're used to right now, as opposed to like, okay, well, what's the pattern that we can use? but I don't have access to like really advanced Rust users to be able to answer that like all the time. I guess like I could make a call out and um ask Avaris or ask oh man, I just forgot their names. Hold on, let's go. F Shoot or Avaris. What they think about it. So if you're listening, and you want to let me know, whether like is this just is the pattern that we see of people using unsafe code so much than talking about it on Reddit, is that because we're trying to force Rust to do something else, or is there a different reason to use unsafe code? Of course, like I haven't got to that chapter yet, so I don't really know exactly the Rust book take on it. So I'm looking forward to when we get there. But until then, talk about ref cells. All right, we're here. Enforcing borrowing rules at runtime with ref cell T. Unlike RCT, the ref cell T type represents single ownership over the data it holds. So, what makes ref cell T different from a type like box T? Recall the borrowing rules you learned in Chapter 4. At any given time, you can have either, but not both of, one mutable reference or any number of immutable references. References must always be valid. With references in box T, the borrowing rules invariants are enforced at compile time. With ref cell T, these invariants are enforced at runtime. With references, if you break these rules, you'll get a compiler error. With ref cell, if you break these rules, your program will panic and exit. The advantages of checking the borrowing rules at compile time are that errors will be caught sooner in the development process, and there is no impact on runtime performance because all the analysis is completed beforehand. For those reasons, checking the borrowing rules at compile time is the best choice in the majority of cases, which is why this is Rust's default. The advantage of checking the borrowing rules at runtime instead is that certain memory-safe scenarios are then allowed, whereas they are disallowed by the compile time checks. Static analysis, like the Rust compiler, is inherently conservative. Some properties of code are impossible to detect by analyzing the code. The most famous example is the halting problem, which is beyond the scope of this book, but is an interesting topic to research. Because some analysis is impossible, if the Rust compiler can't be sure the code compiles with the ownership rules, it might reject a correct program. In this way, it's conservative. If Rust accepted an incorrect program, users wouldn't be able to trust in the guarantees Rust makes. However, if Rust rejects a correct program, the program will be inconvenienced, but nothing catastrophic can occur. The ref cell T type is useful when you're sure your code follows the borrowing rules, but the compiler is unable to understand and guarantee that. So I think what they're talking about here is how Rust will fail. And then we hear that all the time with like, oh, it's a fail safe. And I think like a lot of people don't fully understand like what the different fail and then words mean. So like fail safe doesn't mean that it's gonna like never fail. It means that when it does fail, it fails in a safe method. So Rust, we could say like it either fails safe, or we could say it fails secure, meaning that like when it fails, it's gonna fail in a memory secure way, and not let you do that. So if we want it, if it's getting a false positive, we have to overwrite it. Similar to RCT, ref cell T is only for use in single-threaded scenarios and will give you a compile time error if you try using it in a multi-threaded context. We'll talk about how to get the functionality of ref cell T in a multi-threaded program in Chapter 16. It will fail and not dump all your data out of an error. Yeah, I mean, that's the hope, right? And like, as long as they don't have a bug in the compiler, that's what it will do. Here's a recap of the reasons to choose box T, RCT, or ref cell T. RCT enables multiple owners the same data. BoxT and RefCellT have single owners. BoxT allows immutable or mutable borrows checked at compile time. RCT only allows immutable borrows checked at compile time. RefCellT allows immutable or mutable borrows checked at runtime. Because RefCellT allows mutable borrows checked at runtime, you can mutate the value inside the RefCellT even when the RefCellT is immutable. Mutating the value inside an immutable value is the interior mutability pattern. Let's look at a situation in which interior mutability is useful and examine how it's possible. Interior mutability, a mutable borrow to an immutable value. A consequence of the borrowing rules is that when you have an immutable value, you can't borrow it mutably. For example, this code won't compile. So function main, let x equals 5, let y equals mutable reference to x. Right, because x is immutable itself. Well, we'd have to, we'd have to say that x is mutable, wouldn't we? If you try to compile this code, you get the following error. Cannot borrow immutable local variable x as mutable, because we set it as it's immutable as default. However, there are situations in which it would be useful for a value to mutate itself in its methods, but appear immutable to other code. Code outside the value's methods would not be able to mutate the value. Using RefCellT is one way to get the ability to have interior mutability. But RefCellT doesn't get around the borrowing rules completely. The borrow checker in the compiler allows this interior mutability, and the borrowing rules are checked at runtime instead. If you violate the rules, you get a panic instead of a compiler error. Let's work through a practical example where we can use RefCellT to mutate an immutable value and see why that is useful. This is starting to remind me of an object-oriented getter and setter pattern, where we can just say okay, well, we have this interior vector or some kind of struct, and then inside we can have now change that, but we can't access the full struct itself. We have to access the outside object, which we instantiate from the class, and then we can sort of manipulate it through its methods. A use case for interior mutability, mock objects. A test double is the general programming concept for a type used in place of another type during testing. Mock objects are specific types of test doubles that record what happens during a test, so you can assert that the correct actions took place. This is spine for Mocha and Chai tests with JavaScript. Sign-on is one of the big libraries to use with that. Rust doesn't have objects in the same sense as other languages have objects. And Rust doesn't have mock object functionality built into the standard library as some other languages do. However, you can definitely create a struct that will serve the same purposes as a mock object. Here's the scenario we'll test. We'll create a library that tracks a value against a maximum value and sends messages based on how close to the maximum value the current value is. This library could be used to keep track of a user's quota for the number of API calls they're allowed to make, for example. Our library will only provide the functionality of tracking how close the maximum value is and what the messages should be at what times. Applications that use our library will be expected to provide the mechanism for sending the messages. The application could put a message in the application, send an email, send a text message, or something else. The library doesn't need to know that detail. All it needs is something that implements a trait we'll provide called messenger. Listing 1520 shows the library code. All right, so we'll be creating this. So public trait messenger. So function send gets reference to self and takes in a message that's a reference to a str. Public struct limit tracker, which has a lifetime of a, which is a generic type. Oh, no, wait, sorry. A lifetime, we register a lifetime of a. We also register a generic t type, which is a lifetime of a plus messenger. And then that's a struct, so we have messenger, which is a reference to lifetime of a, generic type, the value, which is usize, and then max, which is usize. Then we implement on limit tracker. So of course we have to bring in the lifetime of a and the generic type. And then we say where the t has the type messenger, the trait messenger. Public function new. So it's going to take in a messenger of type reference to generic type t, also max, which is usize. And we're just going to return a limit tracker that's generic type limit tracker. Then we return limit tracker with the messenger, value, and max. And we instantiate and we set value to beginning to 0 at the very beginning. We also have a function on this implementation of limit tracker, which is public set value. So mutate value self. So we get the mutable self value of the limit tracker. Value is usize. Self.value equals value. So we're just replacing the value with whatever is coming in. Let percentage of max equals self.value as x64. Self.max equals x64. So we're just like changing it. We're not like gonna hit any like, oh, try it again, like increment. If percentage of max is greater than or equal to 0.75, so if we're at 75%, then we send these then we just send these messages when we get to the various places. All right. Let's go ahead and begin implementing this, and we may run out of time because it is 7:48, and we no longer need to be in here. We're creating a library. So in here we're going to call this cargo new -- lib ref cell. Okay, here's our library. I don't think we need any tests right now, but we might be testing this in the project in a little bit. So first thing that we're going to do here, we're going to public trait messenger. So let's go ahead and create this public trait messenger, which that has this function send on it. But all right, pub trait, is it trait with a capital? No, it's trait messenger. Interesting. So it knows and understands that. And so here we're going to just create a function send and send this. And take in a reference to self and a message, which is a reference to a str. Function, what do we call this? Send. So takes in a reference to self and also a message, which is a reference to a str. And we close that with a semicolon because it's the end. That should, yeah, okay. I thought I was getting an error there for a second, but VS Code was just not catching up. So then we come here and have public struct limit tractor. So this is going to be our first full structure. So our public struct limit tracker. Now this is going to have, because we're going to have a reference to A, we need the lifetime of A, but then we're also going to use a generic type. And this is interesting for it. I want to see what the error is when I don't have these. I'm just going to say limit tracker, and we're going to have our messenger, value, and max. So messenger, this type is going to be this reference to the generic type. Reference to T. We're going to have the value and max, which are both usize. Value, size, and max size. So by doing this, we should get an error here which says cannot find T in this scope. So we need to add in T. Then it says missing lifetime specifier. So I also need to have in, does the order matter? Because they put the lifetime first. Can I do this? That. Lifetime parameters must be declared prior to type parameters. So yeah, it actually matters. Order does matter here. Okay. The parameter type T may not live long enough. Note, so that the reference type reference to lifetime A T does not outlive the data it points to. I wonder if it's going to give us a little bit more details about how to fix it. Because like we know what we're supposed to do because the code in the book tells us. But I'm kind of hoping that this will... is it cargo build? Okay. The parameter type T may not live long enough. Consider adding an explicit lifetime bound T:(A). So yeah, it is actually telling us exactly what to do. So that the reference type A2 does not outlive the data it points to. Cargo check. Oh, nice. Okay. So here we're going to say type of lifetime A. All right. So actually, if I didn't like know this from the book, like have the thing there, and I was like just building this, and sort of like the way that I would normally do it, it would walk me through. The compiler would walk me through adding these in here. Also, this bit of code is showing me Rust can be a little bit more verbose than I was originally thinking it would be. Like being able to say like, okay, T lifetime A, like we have to repeat this lifetime A a few different times. Is that what you're talking about? Also, NLL may change this or may not. I don't know enough about NLL to know like exactly what's going to happen with it. Okay. Now we're going to make implementation functions for limit tracker. So I'm going to do the exact same thing and not put on those lifetime specifiers or the generic type, because I really want to like just get used to the compiler walking me through fixing these things, because I think that is one of the best features of this language, because that way I don't have to constantly keep that in memory, my own personal memory, because I just won't be able to. I want to keep other high level things in my memory. Okay, so we're going to implement limit tracker, and we're going to first have, we first need to make sure that we set it so that we only get generic types where this trait is implemented. So where T is messenger, okay, which of course means that I have to use a generic here for T. Missing lifetime specifier, expected lifetime parameter. So it already knows right here. So I have to do use of undeclared lifetime name A. Undeclared lifetime. Oh, I think it's here too, right? And then cannot find T in this scope, so we have to add this in here too. So it found it even faster this time. All right, so we got this. Now function new, public function new is going to be our next thing. So pub function new. This is going to take in our messenger, which is this reference to T. You can see that they worked really hard at the compiler error messages. I remember it being extremely cryptic some years ago. Yeah, some of my friends have told me that as well. In fact, one of them, I think, quit Rust because of that and is now coming back to it. And he says, everything is so much better. It's like a different language almost. Okay, so we're going to take in a messenger of this type, reference to type T. And we're also going to take in the max. Yeah, the max, which is type size. And we're going to return a limit tracker. Is that right? Limit tracker of generic T. Okay, now it's saying, of course, I haven't done that yet. So I'm going to return limit tracker. And in here, we're going to have the messenger. We're going to have the value is initialized to 0 and the max, not macro rules, max. That. So this should now work. Field is never used. Well, that's because I'm never actually instantiating something and not using it. All right, so that gives us that. And then we have public function set value for ourselves. It is 7:57, so I think our next step is right here. Just gonna add set value in right here. And I'm gonna put this line of text in just to make sure that I see, okay, where I am here. Now let's update where we're at, because sort of like in the middle here, which makes it a little bit weird. I think the new Rust team really helped with that. Rust was originally built by someone, but it wasn't going anywhere, so we handed the project to a new team, which they really stepped up. I'm not sure where Rust changed hands in the development stage. Mozilla's just been killing it recently with Rust. I don't know if they started with it or if they inherited it, but they've been doing a really good job. Let's go update this. So cd out. README. Okay, so we're currently at. And if I click on you, hit you. Mozilla inherited the project. Okay, that's pretty awesome. Okay, so we have updated this. Let's go ahead and make sure. Oh, you're not saved. Need to make sure to save you. We'll send everything up, which is creating learning ref cells and pushing that up. This is going to be on the Learning Rust repo, which I currently have links to in the stream description and also the YouTube VOD's description as well. There are some changes in 1.27, and I believe some more are coming to reduce the verbosity. Personally, I've embraced the explicit syntax as it is, but from a coding experience, I can see why they are toning it down. That's one of the problems that a lot of people have with Java, is that it's so explicit. You have to repeat yourself over and over and over again, and sort of drive some people crazy. Okay, so we have the code here. We're doing these streams every single weekday mornings. Tomorrow is not an exception, so I'll be getting up early and at 7 a.m. Mountain Time, continuing on with building out this RefCell library. So it's going to be awesome. If you would like to get notifications when I go live, please follow this stream here, or go find the link to my YouTube account, which I have linked to here, and I also tweet out whenever these videos have gone online and been added to the Learning Rust playlist. With that, I don't think I have anything else, so I'm gonna go get ready for the rest of my day, and I hope that you all have a great rest of your day as well. See ya.